Here, figure shows a rectangular conducting loop of resistance 1.6 ohms. This is a rectangular conducting loop with width 40 millimeter and length 10 centimeters, being pulled at constant speed 1 meter per second towards right side. So this is pulled towards right with a speed of 1 meter per second through a region of width of 15 centimeters in which a uniform magnetic field of 2 Tesla is set off by some electromagnet. I am not showing that electromagnet here. So here when I am pulling this one, first we need to draw the flux, plot the flux through the loop as a function of position x of the loop. Here first of all, what we are going to find, we can find the flux through the loop. When the loop is outside, the magnetic field, then no flux lines or no field lines pass through this one. So the flux will become 0 in this case when this loop is outside. When loop enters into this one, when the loop is inside the magnetic field, then the flux is given by BA, that is magnetic field induction into area of the loop. So that is the maximum flux which is given by, what is the magnetic field induction here? 2 Tesla into area of the coil through which the flux passes, length into breadth. So I am going to write B into LB. What is length here? 10 centimeter. So 10 into 10 power minus 2. What is the width here? The width is given as 40 millimeters. You can write 40 into 10 power minus 3. So the total flux through this coil, or the maximum flux through the coil when the coil is inside this region, is given by 2 into 4. This is 2 into 4, 8 into, remaining terms are minus 2 minus 3, 10 power minus 5, this 0, 0, 10 square. So this is 8 into 10 power minus 3, 8 milliweber. So this is the maximum flux that is passing through this coil when this coil is within this field here. When the coil comes out of the field, once again flux will be 0. So when the coil comes out of the field, when the coil comes out of the magnetic field also, then also the flux will become 0. So I have 3 different values. One is flux through the coil when it is outside, one is flux through the coil when it is passing through this one, and when it comes out. So here I am going to draw the graph. This is the first one. I am taking flux here as a function of x here. When it is outside here, flux is 0. When it enters into this one, some flux here in this position of this coil, some flux is passing this one. So flux gradually increases. When the coil reaches this one, flux will be more. When it comes here, flux is maximum. And here, flux will be constant. Once again, flux reduces. So here flux gradually increases from 0 to some value, maximum value. Then it is constant and then decreases. So what is the nature of the graph for this one? Here I am going to take the position as 0 here, and the flux maximum value is 8 milliwebers. So here I will take 4 milliwebers. This is 8 milliwebers. Flux is in webers. So 8 into 10 minus 3. This is not meters, milli. Or you can write 8 into 10 power minus 3, 4 into 10 power minus 3. When this flux will become maximum, when the entire coil is within this one. So what is this value? The total width of this region is here, it is given as 15 centimeters. Length of this one is 10 centimeters. So till the coil enters completely into this one, the coil has to travel 10 centimeters. So here 0 centimeters, 5 centimeters, 10 centimeters, 15 centimeters, 20 centimeters. So this is 25 centimeters, 30, 35 like this. When x is equal to 0, that means when the coil is outside, the flux through the coil will be 0. When x is equal to 5, that means when some part of the coil enters into this one, some flux will be available. So till it enters completely into the coil, I am showing with the red color one, that is it has to travel 10 centimeters. So till 10 centimeters, the flux will be less than that maximum value. So this is the line that indicates the variation of flux with the distance. After that, when the coil travel to this one, then it is 0, 5, then it is 10, then 15. When it is 15, then magnetic flux will be maximum. Then when it comes to 20, flux will decrease here. So this will be maximum only up to 15. So in this region, till x is equal to 15, magnetic flux will be maximum. Then some part of the coil will be outside and some part of the coil will be inside, till the coil moves away from this one. So for this to happen, it has to travel 25 centimeters till the entire coil comes out of the magnetic field. So this is the variation of magnetic flux in this case. In the second problem, same problem, second part, plot the induced EMF as a function of position of the loop, that is x. What is the induced EMF? According to this formula, we can write minus d phi by dt, the rate at which the flux changes with time. You can also write this as minus of d phi by dx into dx by dt. You can cancel dx, you will get the same point. So this can be written as minus d phi by dx into dx by dt is nothing but velocity with which the loop is moving through this one. So this is the expression to find out the EMF in this case with respect to x. Now this is the flux position graph which we got in the first part of this problem. Now I want to draw EMF and the position. So this is the EMF here, which is measured in volts. This is the position graph, position x, EMF E. Here also I am going to take the same positions here, 5, 10, 15, 20, 25. What is the EMF here? EMF, you can see this one, EMF is equal to negative of the change in flux with the distance, change in flux with the distance into velocity. So first what I am going to write here, from 0 to 10, from 0 to 10 centimeters distance. How to find the EMF from 0 to 10 centimeters? First I need to find out the slope of this one, because this is d phi by dx means opposite side is d phi and this is dx. So this is the slope of this curve into the velocity. Here velocity is given as 1 meter per second only in this problem. So I am going to use this one, from 0 to 10 centimeters. In the EMF is given by minus of the change in flux with the distance. So what is the change in flux for the first 10 minutes? So this is 8 into 10 power minus 3 by time 10. So I am going to write 8 into 10 power minus 3 by, and this distance is 10 centimeters. So I am going to write 10 into 10 power minus 2 into velocity is 1. So EMF is given by, this is 10 power minus 2 minus 2. So 8 by 10 into 10 power minus 1. When this goes up 10 power minus 1, 8 into 10 power minus 2 volts. So this is the EMF induced from 0 to 8. That is the maximum value here. Now from 10 centimeters to 15 centimeters, you can see the flux between 10 to 50 centimeters is constant. It is not changing. Whenever flux remains constant, EMF will not be induced in the coil. So from 15 to this, flux is constant. So EMF minus d phi by dt will become 0. We know derivative of a constant is 0. Now in the third case, from 15 to 25 centimeters, here the flux is decreasing here. So we can write EMF induced is equal to minus of decreasing flux. Here theta is negative because it is anti-clockwise, this is clockwise direction. So decreasing flux by final flux 0, initial flux is 18 minus 3. So change in flux will be minus 8 into 10 power minus 3 by this distance, once again 10 centimeters. So 10 into 10 power minus 2. Directly you can write minus of minus plus here, but here you will get minus here. So this is 8 into 10 power minus 2, but this is positive here, this is negative here. So these are the EMF induced in this position. Now in the first 0 to 10, you can see EMF is negative. That means we need to extend this graph in the downward direction also. So what are the maximum values of EMF? I am denoting this as 8 into 10 power minus 2. So this is, let us say this is 4 into 10 power minus 2. This is 8 into 10 power minus 2. This is minus 4 into 10 power minus 2. Minus 8 into 10 power minus 2. So from 0 to 10 centimeters, as there is a continuous change in flux, EMF will be constant, and which is equal to up to this position. This is the EMF induced here. So as the flux is changing, EMF will be induced throughout this one. Then suddenly this EMF will become 0 here between 0 to 15. So this is the flux here. So after that, from 15 to 25 centimeters, EMF will be positive. So I am going to take this value. So this is a positive value here. So this is the positive value. Now we can complete this graph like this. So this is the variation of EMF. First it was negative, and then it is 0, and then it is positive. The third part, plot rate of producing thermal energy in the loop as a function of position. In these two graphs, here the flux after 25 centimeters will be 0. So I am not drawing that one. Actually we have to draw that one also. After that flux continues to be 0. Here also after this 25 centimeters, this flux, this EMF will be 0 here. Now the thermal energy. Thermal energy is nothing but the power produced, rate of producing thermal energy. That is nothing but power, which is equal to E square by R. Now from 0 to 10 centimeters, the EMF is minus 800 minus 2. So what is the power from 0 to here? From 0 to 10 centimeters, the power is given by EMF minus 8 into 10 power minus 2 whole square by resistance of this coil. Here it is given as 1.6 ohms. So this is 1.6. So power is equal to 8 8s are 64 into 10 power minus 4 by 16 into 10 power minus 1. 16 1 so 16 4. So this is 4 into 10 power minus 3 watts. So this is the power in this case. After that, what is the power here between 10 to 15? As there is no EMF induced between 0 to 15, 10 to 15, here 10 to 15, the power is given by 0 square by R, which is equal to 0. Here power is equal to 4 milliwatts, here power is 0. From 15 to 25 also power remains as it is. Why? Because the EMF is here positive, square of the positive value remains as it is. So what is the nature of the graph for power here? In between I am going to draw those two. For the same distance, the power will be, first it is 4 milliwatts. So let me take this as 4 milliwatts power. This is 0, 5, 10, 15, 20, 25 like this. From 0 to 10, the power is maximum, which is equal to 4 milliwatts. After that power will become 0 here between 10 to 15. Once again rises and up to 25 it is maximum, which is equal to 4 milliwatts. After that it is 0. So these are the three corresponding graphs for three different quantities here. This is the flux value, this is flux graph, this is induced EMF, and the middle one is the rate of produced thermal energy, that is power. Problem. Calculate the induced EMF in a square coil at a given moment. So there is a wire carrying some current capital I here, and nearer to this one at a distance r, a square coil of side A is placed which is moved away from the wire with a velocity v. So what is the induced EMF in this case? To find out induced EMF, we have this formula minus d phi by dt. First of all, before finding EMF, let me find the flux passing through this one. And already we know that whenever current is passing through this one, field inside this one is into, nearer to the wire field is maximum, and if you move away from this one, field changes. So here field is changing, so automatically flux changes. The flux is given by B dot A bar. This is the total flux. But if you first let me find out a small flux passing through a small strip of this one. So here I am taking a small area of this one. So this distance is x and this is equal to dx here. What is the area of this strip? This length is L because sides are same for a square. This length is A and this width is dx. So area of this strip is equal to area of strip A into dx. This is the area. Now here what I am going to write, what is the magnetic field at this point due to this current which is acting into this one? B is going by mu naught I by 2 pi, from here to here distance is x, 2 pi x into area of the strip is equal to A into dx. So this is d phi. So what is the total flux passing through this one? Integrate on both sides to get the total flux here. The total flux is given by, bring the constant terms outside, mu naught is a constant, current through the wire is constant, 2 pi is constant, length of or side of the square is also constant, remaining terms dx by x with the limits. What is the minimum value of x here? Minimum value of x is equal to r, maximum value of x is equal to r plus a. So here this is r, this is r plus a. These are the two limits here. So the total flux is given by mu naught I by 2 pi, mu naught Ia by 2 pi. Integral of dx by x is log x. So I am writing ln x with the limits r to r plus a. So the total flux is given by mu naught capital I by A by 2 pi. This is ln r plus a minus ln r. So ln r plus a by r. So this is the flux passing through this one at that given moment. Now I am going to find out the EMF E is equal to minus d by dt of that flux mu naught Ia by 2 pi ln r plus a by r. So this can be written as minus d by dt of, first bring the constant outside also, here also. I am differentiating this one, that part is integration, this part is differentiation. Mu naught constant, current constant, a constant by 2 pi. Now this is minus d by dt of ln r plus a by r by r is equal to 1 plus a by r. So this can be written as minus mu naught capital I by a 2 pi. Now differentiate this one. This is in the form of log x, which is equal to 1 by 1 plus a by r, because log derivative of log x is equal to 1 by x. Now chain rule, derivative of 1 is equal to 0, derivative of 1 is equal to 0, plus a is constant, r is the variable here. As the coil moves away, r value changes. That's why 1 by r can be written as minus 1 by r square, and the derivative of r with respect to time is dr by dt. So to solve the problems in physics, your basic mathematical knowledge should be strong enough. Now after getting this, I am going to substitute these values now. This will become minus of mu naught Ia by 2 pi. This you can write r plus a by r. So this is R by R plus A here outside, and the inner values here are, this is minus A by R square, minus A by R square into, what is dr by dt? The change of this R value with respect to time. When it is moving the velocity v, dr by dt is nothing but velocity of the loop. So here in place of dr by dt I am going to write velocity of the loop. Now you can see one minus here, one more minus here, minus of minus plus. So you will get mu naught capital I A by 2 pi R by R plus A by R square into V. You can cancel this R and R here. The remaining terms here A into A square. So mu naught I A square by 2 pi R into R plus A into V here. So I am writing here V. So this is the EMF induced in this one. And from this equation we can see that EMF induced in a coil, that square loop, is directly proportional to the velocity with which the square loop is moved away. Why? Because mu naught constant, current constant, square of this is area of the loop constant 2 pi. These are all variables, but this is another variable which is changing here. So velocity will give, or the EMF will induce, will depends upon velocity.